Welcome to today's training on Midas GTSNX, a finite element software for solving geotechnical engineering problems. Today's tutorial will be on how to model a 3D excavation and also how to install a piled raft foundation. So this will be a construction stage, construction sequence analysis, and we will be doing both the excavation and installation of structure. So we will go through the steps of how to model the 3D geometry, how to set up the four excavation stages, as well as how to install support elements like a wall and a raft with piles. And additionally, we will also be showing how to include interface elements that allow us to better simulate the interaction between the ground and the structure, which also includes the pile element, which is also an interface element that has even pile tip properties. So here are the summary of the materials used. We'll be using three ground materials: sand, sandy gravel, and clay, all with the Moore column constitutive model. And here are the structural materials. So we'll be using concrete for the raft and for the wall, as well as this being the pile element, which is a pile interface element. And lastly, we will use the wizard for creating the interface between the wall and the soil. So for today's training, the files included have a start file, which is the one we're going to open. And from there, the materials are already defined. We'll give it a quick inspection just so you know where you can add additional or modify materials. But we will take off from the starting file that already has these defined. So we won't be going from them from scratch. So opening the program, the start file. This is Midas GTSNX. This has what are the commands based on icons, and they follow a logical sequence from left to right. So starting from all the geometry commands that are similar to AutoCAD and then going on to the next tabs. For instance, in the mesh tab is where we have our materials defined. As I mentioned, in this case, the materials have already been defined. If we wanted to create a new one or modify one, we can just select it from the list and go to modify and give it a quick inspection. If you wanted to use more advanced constitutive models, for instance, for clay, we have some other ones like the modified cum clay or soft soil, or you can even use your own constitutive model. And then you would also just tell the program how these materials will be used, which is what the properties are. So we see that our soil layers will be 3D solids, where our wall will be a shell, 2D shell, and then our piles will be 1D beam elements. The program has actually a pretty substantial database for structural sections, which is a big advantage. So we can even actually go here into the section template for the property, for instance, for the pile, for instance, and say you wanted to do an H section pile instead of just a solid round pile. Well, you can give it the dimensions that you want manually, or you can select some sort of international like standard or code and then select the list from our large database. In this case, we'll just keep it where the original round. So we can now start with the tutorial itself. Another introduction to the modeling in GTSNX for the geometry is that we have this plane, what we call the work plane. This work plane is something that helps us draw on a 3D environment, since it can be hard to pinpoint exactly how or where the depth of something is in a 3D space. And it can be turned on or off. It can be modified in size. For instance, here we have spacing of every 20 meters. I can make it much smaller every meter or so. And I can also vary its dimensions, how far I want it to spread out. And lastly, I can also change what plane it's on by going here on the work stream and having like a double click. So now that when I ask to see the normal view to my plane, I'm actually looking from the top view. And I can zoom in. So this plane allows me to draw directly on it, but I know exactly where the drawing will be on, especially 2D drawings. So this is what we're going to start off with. We're going to start drawing rectangles that will be the top surface of our soil layers and excavation layers, and then we will extrude them down. So I could go back to the top view and zoom in by scrolling with my mouse. And then I'm going to go to rectangle. And what I want to do is I want to create two rectangles, the outer boundary layer and then the inner excavation layer. Now I can do this by inputting coordinates directly, or I can just select on my grid 2 points. So that being the origin, as I'm spreading, this is updating automatically. So I want to go to 60-60 to make my first point. So it's somewhere up, almost. Okay, so there we are at 60-60. I've drawn the first rectangle, and the second one, like I mentioned, you can also just input directly by coordinates. So I'm using the two corner system, so the left bottom corner will be at location 1821. I press enter, and then now it's asking me for the second point, 2418. So we see that it's also created the second rectangle there. In this case, I'm working in kilonewton meters for my units. So I can now deactivate the grid, go to the isometric view, and we see we have the two rectangles. So I can now proceed to the other parts of my geometry. In this case, what I also want to do is create the points for what would be the piles. And so for this, I can again draw on the grid carefully points, but the program also allows me to copy list from Excel of these coordinates. In this case, they're all in the same plane. As we can see, the depth is at almost 10 meters, but it'll give me the coordinate location of all these points. So as I mentioned, I can turn on the grid and draw specifically points of where I would want my pile locations to be, one by one, or we can use this other option called tabular input. And what I mentioned was I can just copy paste directly, and we see the program has now allowed me to input what would be the location of my piles, specifically the pile heads. So from here, I'm going to start creating 3D geometries out of these lines and points. I will use commands like extrude. The first thing I want to do is I want to extrude my piles from these points. So seeing how we have here different kinds of geometries, we actually have also selection filters. So in this case, I can tell the program that I want to select points, and I can just draw a rectangle. In this case, I very carefully only want to select the points related to the piles. And I'm going to protrude them, extrude them, so I'm going to make lines out of this. I'm going to select the direction to be in the vertical, and I'm going to give it a distance. I want my piles to be 10.3 meters long. And I have this preview command, and I can just go ahead and click here. And if I do a side view, we now can see that the lines for the piles have been creating out of these points. Well, I'm going to repeat the process to make the solids out of my model. And so we can start selecting these different geometries to make the solids. We'll start off with the excavation, the inner excavation. So again, I'll go to extrude. This time my selection filter will be lines or edges, and I'll select the 4 edges of the inner excavation. Again, I'll do it in the vertical, and I want to extrude the first excavation to be 3 meters deep, and I can again preview this. I can then rotate the model using the scroll button on my mouse, select the bottom face of this, select again the vertical direction, and extrude it another 4 meters for the next excavation layer. Repeat the process. For the third excavation layer, I want to go another 3 meters. And lastly, I want to select this face one last time, and we'll have a fourth excavation, but this will also turn into the raft at a later point. And this will be almost half a meter thick, 0.6 meters thick. And then we repeat the process for what would be the outer excavation layer. I will go to extrude. This time the outer layers, the first one would be for 3 meters. The second layer will be for 15 meters. And the last layer, so here I'm selecting again just the bottom faces. Will be another 20 meters. Oh, gotta give it a direction. And this preview command is pretty handy for that as well. You're just making sure you're going in the right direction. So now that we have the final shapes, the very crude shapes, actually I want to select the outer 3 layers, and I can right click on my mouse, and just to show you different ways of viewing things, we can actually change, for instance, the transparency. I can make it half transparent, and we can see a little bit of what's happening inside. I can also again select all the geometries, right click, and I can even, for instance in this case, give it a random color to all the different layers, so it's even easier for me to identify, to see what's happening inside. So next what we want to do is, at this point, all of our geometries are not in touch with each other, to say it crudely. So this geometry doesn't recognize, or this geometry doesn't recognize that there are other geometries inside. So there are different ways for the program to acknowledge this or to receive this command, and we can also check it before and afterhand what's going on. So for instance, if I was to say I was done with my geometry and I wanted to proceed to start meshing, but I wanted to check if the program had recognized these connections beforehand, before I meshed, and I didn't have to start all over. Well, we have a tool called check duplicate, and check duplicate allows us to see what the program is recognizing in contact. So, and it lights them up in orange. So for instance here, we see that the faces in between layers and even inside are orange. So the program is going to connect these layers to each other. But the program doesn't have any of the vertical walls inside lit up in orange yet. So the program wouldn't be connecting the excavation to the outer soil at this point. We would have to correct for that. So there's different methods to do this. We can divide solid by other solids, or by surfaces, or we can use Boolean operations to embed an object into another. In this case, because it's a very simple geometry shape and it's a very simple, straightforward, just excavation, solid within a solid, we can just tell the program that we want to just connect the solids to each other. This is at the geometry level. And so I will use the Boolean method, and I can just select all the solids, the 7 solids, and tell the program to connect them. So now we see, if I was to deactivate one of these geometries, for instance the first excavation, we see now that the program has recognize that there was going to be an excavation in there, and this outer geometry is not it's not overlapping anymore. So it has the correct shape. And again, if I go back to this check duplicate, now we see the difference. Now we see that even the vertical walls are lighting up in orange. So the program has now recognized the contact, the excavation geometries inside the outer geometries. And so we could proceed to mesh. Now, in some instances, you want to have some control over the size of your mesh. You want to, for instance, be able to give perhaps a smaller size for more accuracy in the elements on the inside than for the elements on the outer boundary that can be larger, so that you will overall have a smaller number of elements. So the program allows you to do this changing or varying of size controls by using this command right here. So rather than have a global size, I'm going to change or give specific sizes, specific divisions to some of the elements or some of the areas. So I'm going to select only the inner lines and tell them that I want. So we have different methods here. I could tell it every 1 meter or every 5 meters, give me a node, and if I go to preview, it'll show me the distance between them. Or I can actually tell it by divisions. So I can tell it, I want you to divide this line X amount of times. So in this case, 10 times, for instance. And so it would show me, we can see here the little icons of where these nodes would be placed. So we want to do that actually for the inner and the outer boundaries. So again, we go to the preview. But we also want to be careful not to select or to deselect the vertical lines, since that will be controlled by the direct meshing. So I'm only trying to assign this command to the horizontal lines. And it looks like I just have to deselect that one as well. Right there. Okay. Actually, so this selection method has also selected the inner vertical lines. I'm going to undo this command. I'm going to go to the top view again, and I'm going to do a different selection method that will make it easier for me to guarantee that I'm not selecting the vertical lines, only the horizontal lines that I will cross. So I'll go back to size control. Again, I will select the method of 10 divisions. But what I'm going to change this time is the selection filter. So we see here that up to this point, I've just been drawing rectangles, but we have different ways of selecting shapes in the program. So if I use this, this creates a line, and anything that is intersected by the line will be selected. So in this case, it's much faster and much easier to only select the horizontal lines, since that's the only thing that has been crossed. And now when I apply this command, we see that the vertical lines don't have this imposition of the number of divisions, only the horizontal lines, which is exactly what we want. So now that we have the size control, we can proceed to start meshing. I will first mesh the inner soil layers. So I will rotate this model and select these 3 layers and then turn them off here in the work stream. And I will now change my selection filter back to this. I actually want to also get rid of some of these other curves in the meshing. So we can go ahead and go to generate 3D. And in this case, we will do by layers. I will give it a size of 1 meter, and I will use the type of element hybrid. This is a topsoil excavation, and it will have topsoil material. I'm going to call this excavation 1. This is now excavation 2, but it actually has the material for mid-soil. Then we proceed with the other two. So these two other layers of excavation have the same material. There will also be the mid-soil material. This is excavation 3. And this is excavation 4. And I'm also going to call it raft. So what's going to happen is the original layer will be soil. We will go through the process of excavating it, and then subsequently in a later stage we will reactivate it with the material property of concrete. So this is why this layer will actually have two different materials at different stages, and we will show that later using a boundary condition command on how the program can do this, specifically for these kind of analysis that require construction stages. So we don't mesh the same geometry twice, we simply give it a boundary condition with different material properties. So we now proceed to mesh the outer layers. For this, we'll give it a larger size. I'm actually going to tell it by number of divisions. I'm just going to tell it to give it a number of 3 divisions. This is topsoil, but this actually will have the name topsoil. This will be 5 divisions, and this will be mid-soil. And here we have the progress bar of the generation in progress. And then lastly, this will be the bottom layer or bottom soil. We change the property and we call it that. Okay, so we're done with the initial meshing. We can actually check how well these layers were connected. Well, one is to give it a visual inspection, and we can clearly see there is a change, a gradual change in size from the outer boundary to the inner boundary of our soil, and you can actually see the connections line up. You can see the squares of the blue to be around lining up around the same size of the smaller squares in purple. So a quick visual inspection lets us know that it looks connected. But we have another tool in the program called mesh check. So we can go to check, and we can tell it to show us the free faces. And what I should only see should be outer boundary of my layers. If the inner layers meshed were not connected to the outer layers, then I would actually also see the rectangles or the cubes inside, telling me that these are not free faces, that the program has not connected them properly. But because here I only see the outer boundary, it tells me that the program recognizes that everything is a single mesh and it's all connected. So I can now proceed to the next step, which would be to extract or generate my walls. For this process, it's actually easier for me to do this at the geometry level. So this is why I'm reactivating the solids and deactivating the mesh. And I'm actually gonna, again, deactivate the soil layers. I only want the inner excavation geometries. So to do this, I will go here to extract element, and in this case, we want to select the type face as the type of geometry we can select. And so we see here that I have now the property that I will be assigning it is the 2D shell element with the property wall. And all I have to do is select the faces on the outer side of my excavation. And the program will, as the command says, extract the location of the existing nodes of the soils, but assign the material 2D shell. Hence, we see here now that these elements will automatically be connected. There's no issue about the connection for this new wall. So I can now proceed to add the next phase of this, which would be, I want this wall to have an interface. I want to simulate the behavior more closely between what is happening, the interaction between this structural component and the soils around it. So for that, we have the interface element. The interface element essentially is a series of springs that are put in between the nodes that connect the soil to the structure, in this case the wall. So right now they are rigidly connected, but by adding this interface, I am breaking that rigid link and adding these springs that have properties for stiffness that allow us to see that behavior that would be like the skin friction between the soil and the structure. And this can be defined manually, or we also have a wizard that has the following components: a ritual thickness and a strain reduction factor, that allow us, based on the different material properties, to have a range of values for this. This is similar to other programs like Plaxis, and can actually be kind of quickly seen. This PDF is actually also included with the material, so you can look through this slide. So this is what the parameters the program uses to calculate these K values, these stiffness values, Km being in the normal direction of the wall and T being in the tangent direction. So these are the equations the program uses, and then there's suggested values, range of values. For instance, the TV should be somewhere between 0.01 to 0.1, the range depending on the stiffness difference. And then for the R value, the other value that we input, it also depends between what kind of structural material you're using. In our case, we're using concrete, and what the value or what the type of soil we're looking at. In this case, we're using both sand and soil, but most of the excavation is actually happening in the sand. So for this tutorial, we will use a value of 0.1 for the ritual thickness and of 0.8 for the strength reduction factor. What we also want to do is we want to create rigid links. So these rigid links will be temporary, but because this is a construction stage analysis, we won't be installing the wall into a second or third stage, which is when the interface will also be activated. So in the meantime, we need something to still have the connection between the soil elements that are going to be eventually disconnected by this interface in order to give stability. So these rigid links are created and activated in the initial stages and then replaced when we have the interface itself activated. So that's that component. It's in those matters. So we'll quickly just do this, give it the right reduction factor. I will select, actually from the method I want it to be from the shell element. So I can just select all the elements, and I want an interface on both sides where we can actually decide if we only wanted it on one side. For instance, normal will be on the outer, negative normal will be the inner. And this last command for merging nodes at the base is to give it stability. So we select all the nodes at the base. From the side view, I was able to select all of them. I have to do the wizard, just inspect it one more time, select that method, and create the rigid links. So now the interface, you can see the icon has been created, and I also have a set for the rigid links. So now we can proceed to mesh the piles. That's the last part that we need to do, the structural components of the piles. I will reactivate the curves related to the piles. I'll put a side view, and I will go on to mesh or generate a 1D element. So in this case, first I am creating the structural component, which I'm going to tell it to use a beam, and I'm going to tell it that I only want the element to be quote unquote divided once, which basically means it's not divided. I'm telling it as I do the preview that I just want a node at each end. It's basically one long element. So this is the beam element, beam pile. And as we saw, it has it's just a concrete pile. And now I can actually even preview the diameter of this. If I go here to my structural, to the property tab in the worktree, I can activate it and I can visually see the piles. So again, they're 1D elements, but they have the structural property of a cylinder pile. And now we'll add the pile interface and pile tip element. And these are similar to what we want to see with the wall, elements that better capture the behavior between the pile and the soil itself, the friction and the bearing. And they do this, we in this case have defined two, but we're only going to apply the pile to soil interface. And the pile soil interface have the following components. If you were to expand on the materials, so we have an ultimate shear force and a shear stiffness modulus as well as a normal stiffness modulus. So the shear stiffness modulus corresponds to the linear component of the line of the graph, while the ultimate shear force is basically the ultimate shear resistance it can take. And so these can be captured or found through different methods. We recommend doing it through loading tests, lab test results, but there's also ways to calculate this by hand using the formulas from the wizard. So similar to what we saw for the wall interface with a strength reduction factor and a virtual thickness, you can get similar approximations for what would be the pile interfaces. So the online manual has a detailed explanation as well as for the pile tip element itself. And so we will select the pile soil interface, apply it to all our piles, just give it a name. What we want to do is we want to simulate the pile tip. And similar, this is actually also a spring. And so we can assign a specific bearing capacity and stiffness. You can even do functions for this. So we just select only the nodes at the bottom. So again, I give it a side view and then I draw a rectangle and I'm assigning the pile tips. So we now have all our structural components in place. And we can proceed to start adding other things like boundary conditions and loads. So in this case, I would first assign the boundary condition to the soil layer. So I'm going to go here to the next tab and select boundary constraints. So the program has different methods for applying these. You can manually select nodes and restrict degrees of freedom in rotation and displacement. But you can also tell it that you want to do like an automatic application of this. You don't have to select anything. The program will automatically find the outer boundary of your model and restrict the correct degrees of freedom in terms of which direction it's not supposed to move. So you can kind of see from the icons that the arrows point in different directions on the walls, whereas in the bottom they're actually restricting in all three directions. So that makes sense. What we also want to do is actually stabilize the piles, stabilize the analysis by applying a restriction in rotation in the Z direction for the piles. This is just for stability. So I select all the piles. What we want to do next is apply the loads. So first, of course, would be self-weight. Basically, gravity, all you got to do is you tell it the direction of gravity is in the vertical Z. And we'll have a big arrow there. I'm now going to move in the workspace to the analysis tab and deactivate these. What we also want to do is apply a load to the raft itself to simulate the structure. So I'm going to deactivate all my sets and only activate the one for the raft. So I'm going to apply a pressure load. I'm going to apply this to the face of the top face of these elements. So I'm going to select the object type as 3D element face and put a side view. And then just select or draw a rectangle that only selects the top faces of this raft. And I'm going to apply a load of 200 kilonewton per meter square. So we can just call this the raft pressure. And it's automatically going to do it in the normal direction. So we see that there. And what I also want to do is I want to use this command, a boundary command called change property. And essentially what I'm doing is I'm telling the program that, yes, initially this raft has the material of soil, but later I want it to be considered a raft itself. So I can select other material properties and apply them to objects. In this case, I'm going to select the raft. And we see the icons there that will allow me in one of the stages to later see the behavior of that as the raft itself. So we now have all the model ready. And what we can do now is proceed to define the analysis stages. So we can go here to construction stage, stage set. One thing in this tutorial we don't cover it, but if you wanted to assign water levels, water tables, you can easily apply it here, and you can apply multiple water levels and have them in different stages at different heights. So you can actually simulate dewatering of the excavation site applying these water level commands. But for this tutorial, we won't look at that. So I go to define the construction stage set first. We see that we have different types of analysis you can model in stages, including like just seepage or semi-coupled, like where you have a variation between flow and stress analysis, consolidation, even what would be a stress, and then a seismic analysis. So for now, we're only working on stress. So I click add. And once I've added it, then we'll see that it's created here in the window. I have to select it in order for these other commands to turn on. And the command that I want to use is this define construction stages. So this opens this next window. And we see here that we have 3 tabs. And it's clear that this first tab is like the works tree. It's summarizing all the sets that I've made in my mesh, all the loads that I've created, and all the boundary conditions. The other 2 are active and deactive windows. So I will drag from left to right throughout the stages to either activate or deactivate things in my model. This might be a little confusing, especially when you have many stages to keep track of, just my memory. So a trick for that is to change the filter here on show data to show only what's been activated up to this point. So we see nothing has been activated. So as I start to drag and drop from left to right, things start to appear. So the very first stage is just the initial stage, or in situ stage. So nothing has happened yet. And so we want to activate only the soil layers. So I want to activate all the layers that will be eventually excavated, including this one that will eventually turn into the raft. But as we remember, it now currently has the soil properties. And then the 3 soil layers. No structural components, no wall yet, just the soil layers. What I also want to include are the rigid links for the wall interfaces. As I mentioned, the wall won't be installed into the next stage. So currently these nodes between the inner and outer soil layers have to be connected somehow, and that's what the rigid link is for. I activate the boundary condition, and I activate the gravity load. What I also want to do is I want to clear any displacements that might be caused by internal stresses or current stresses. What I only want to see is what's happening based on what's going to be happening in future stages, like the excavation. And here's where I could define or activate the water levels. So had I defined it manually and selected different levels, I would have created here some sets of water levels that I could select, or I could also just give it a global size based on the origin. So if I give it a water of 0, the water level will be right at the top. So for now, again, we're not going to use or consider the water pressure in our analysis. We're only going to worry about the stress components of the excavation itself. So then this would be the first stage, and I now go to new. This new stage is the wall installation. So I will drag and drop the wall into place. I will also activate the interface that comes with this wall. We can see it there. But now that the interface is in place, I no longer need the rigid link that were created originally to stabilize the model soil layers. So I can drag and drop all the way to the left to deactivate, since it was activated in the previous stage, but I don't need it anymore. And again, I could clear the displacements here, since there are going to be some displacements created initially by the installation of the wall itself. And this is only because I care more about what's happening due to the excavation process, not so much about the wall install itself. So now to proceed, we will start to excavate. So this would be the stage where I have my first excavation. So this would be excavation 1. And I'm just going to drag and drop the set called excavation 1, and we see it here disappearing or being deactivated. Save, new stage, excavation 2. I do the same, drag and drop. And so I proceed like this until I get to the final excavation stage. So next stage, excavation 3. And lastly, we're going to have the excavation 4. So again, right now I'm deactivating or doing the final excavation, but then in this next stage, I'm going to install the raft. So what's actually going to happen is I'm going to bring back the same set. We see it appears here again, but now I'm going to apply this boundary condition, which is basically telling the program that set is now concrete. It's no longer the material property of soil, but now it's now concrete. What I also want to activate are my piles. So I'm installing it all in the same stage. And so if I have the piles, I also want to have the interfaces as well as the stability component that I had applied to it. So this is would be the raft stage. And then the very last will be the load, the pressure load stage. So we've created all of our cases, and now the last thing we need to do is tell the program that we want to run the analysis to be construction stage. So I can go here in the workstream, click analysis case add, or I can just go in the tab for analysis and go to general. It opens the same window. Here we have a list of all the analysis the program can do. So we see the program can do all kinds: static, seismic, slope stability, seepage. In this case, we're doing construction stage. We've only created one case, one set of construction stage analysis. So in this list, there's nothing else to select. And then in analysis control, I have to tell the program that I want to consider the K naught condition, which would be basically the earth pressure, lateral earth pressure. And by default, the program doesn't include the strains in the results, but we can actually just manually go to output control and tell it that we also want you to calculate this. And then you just run the analysis. You can just go here to perform. You would select the case. In this case, there's only one. And the program will start calculating. And you can see the progress in this output window. You can see everything that's happening throughout every stage as it's going through. And in the end, it'll give you a message about how much time it took to run, or if there were any warnings or any errors. So we see here that it's going, and it's in the very first stage. It's performing the analysis, and you would see the progress of every single stage in the process. So then here it says 11 seconds in that stage. It's now on to the next stage. In order to save a little time, I'm just going to go ahead and open what would be a model that's finished running. So what we are looking at now is that I'm no longer in the pre mode, I'm in the post mode, which is the post processor, which you see all these commands are locked, but if I go to the results tab, these are now open. Similarly here, if I go to the results tab in the worktree, I have all my commands, all my results in this order of the stages, so I can expand and see particular results for each stage. So for instance, I could go to the very last stage, and we see we have many more options to test our results in the last stage. That's because it's also grouping by type of element. So in this case, at the last stage, I already have my piles and my walls, which is my shell and my beam element, as well as some interfaces. Whereas in the first one, I haven't installed them yet, so that's why these don't appear in the other stages. So let's take a look, for instance, at the total displacements at the very last stage. So here we have a kind of an idea what's happening, but we don't really clearly see what's happening as well. I can activate or exaggerate the formations. We have a sense, I can change the units. So we're looking at around 33 millimeter displacement. If I wanted to get a closer look, I might actually consider slicing or clipping my model, because for now, at this point, I could only kind of see what's happening and try to pinpoint, create these probe commands to have an idea of more or less of what's happening at some places. But if I really wanted to get a better view, we have different commands like this clipping plane. Then I can add around different directions. So for instance, I can add a clipping plane in the X, and I can add a clipping plane in the Y. And then in the end, tell the program that I either want to see the corner of it or I want to see cut out that corner. So here now I have a much better view of what's happening, all the displacements that are happening around my model. And this bar at the bottom actually works very well for construction stages. If I go left on my keyboard, I can go through the whole process. So this is the first stage of the excavation, second, third, fourth. Now the raft has been installed, and now the load has been applied. So you can kind of go through that process with this bar at the bottom. I can also look at create bulbs based on the range of results. So I will deactivate the clipping plane and show you a different command we have, which is the isosurface value. So this command activates elements based on the range of values. So for instance, if I wanted to see only what's been deformed below, or what's deforming more than 3 millimeters, then I can create this range and it'll start showing me these bulbs. So that way it kind of gets rid of whatever's not happening of importance around, but I can focus exactly on what I want to see. I can also modify a little bit or clarify a little bit the color, so I can give it like an auto range, and the program will try to better reflect what's happening and get rid of what's not. So now if I do the clipping planes again, the colors are more intense and more vibrant. So for now, I can also change the way I look at things. I'm looking at clear fringes of ranges of colors, but I can just do a continuous and it makes it look a little cleaner. I can also change the edge type if I want to see the meshes reflected more carefully. And lastly, what we can start looking at are the other kinds of results that are important. For instance, let's you know go to the beams, and we want to see the actual forces on our piles, or the moments. So all this, it's grouped by type of element. Similarly, for the wall, we can look at the forces or the moments in the different directions of the wall, reflecting deformation. We can more easily visualize some of these things by applying what would be diagrams, or as we had done before, just probing directly. So I could isolate only the wall in my mesh set, and then select the nodes around the surface of this. If I wanted to extract this into a tabular or table format, as I mentioned, I can also do diagrams, what we call cutting diagrams. I could just select 2 points of interest along, for instance, the side of the wall, and tell it a direction that I want this to be shown. So here I'm looking at the range of results. It might be easier to see it if I reverse this direction. So here this diagram is showing me the negatives and the positive bending moments very clearly now. And lastly, let's just say that if we wanted to graph or extract some other kind of result, like the maximum displacements throughout the process. So for that, we have one last command we can see, which would be, there's the diagram a little more clearly. So let's go one more time to, let's say, the displacements. So for instance, let's say you just wanted to get an idea of what are the maximum displacements in every stage. You can go to this command, extract, select the type of result you want. Let's say just displacement, total displacement, and we only select the stages related to excavation. And we tell it, we can select points of interest, or we can directly tell the program, just tell me the maximum, what's happening, what are the maximums at each stage, and give me a table format of that. And the program will then put this output for you that you can then select columns to graph either in Excel or directly graph in the program. And you can get an idea of what's happening in terms of whatever result you choose. So the program has all kinds of results, stresses, strains for even the solid elements. So at this point, we've only been looking at displacements, but they're grouped over here. So you can look at other, principal stresses or other results like the max shear, pore pressure, stuff like that. So everything is grouped depending on what kind of result you're looking at. We can even look at plastic status of the material. So we can see here where the plastification is. Especially looks like the longer walls are having a harder time, but even the shorter ones in the middle. And so here would be also the strains. So we can get like the max shear strains or other kinds of principal strains, stuff like that. So this might be better for the bulb, the ISO surface command to give us a range of the strains and potential areas of, let's compare this to what the plastification was. But that would be the conclusion of this tutorial. This PDF will be included. We just did all these steps. And so in the very end, we will just, we went over all the different methods of looking at the results, setting up the analysis, and stuff like that. All the stages that we saw. as well as we mentioned different diagrams, cutting planes, and so on, looking at the results, structural results, the walls and such. But that would be the conclusion of this tutorial. Thank you very much for your time.